HT in the inlet, and then finally the inerts, FA naught theta I. I ran out of space. HI in the inlet minus FA naught times 1 minus conversion times HA naught. So all we're doing is using those equations over there, right? For FA, FB, FC. Yeah, I just realized it. We're on the same wavelength. I started erasing. Yeah, the enthalpy should be the exit enthalpies, not the inlet. And all of this is inside your subtraction. I'm going to run out of space. But I think you guys get the point, so you can do it correctly in your notes. Conversion times HT, and then one more term, which is FA naught theta I times HI. So we can simplify that. And what you get is FA naught. All of our terms have an FA naught in them, right? So we can factor FA naught out from everything. And then you get HA naught minus HA. Right? Too damn big. You might be wondering where the conversions are. That's because we're not done yet. This equation is like 18 lines long. There's your conversion. All right. Any questions about that algebra? Okay. This bit right here is what? Well, we can write it out. It's the sum of the stoichiometric coefficients times the enthalpies, the molar enthalpies of those streams, right? What's that equal to?
Enthalpy of reaction. Enthalpy of reaction.
Say that again?
Enthalpy of reaction.
Enthalpy of reaction, yeah. All right, anybody remember calculating that a long time ago? Just, no? Yeah, maybe, hopefully. Products minus reactants, right? The enthalpies of each product minus the enthalpies of each reactant, multiplied by their stoichiometric coefficients, you get the delta H of reaction. Now, does that change with temperature? Yes. Okay. All right, So delta H of reaction at some temperature. Like I said, it's equal to the sum of, for each species, stoichiometric coefficient times the molar enthalpy of that species at that temperature. And what temperature do I need for these enthalpies? Are those the inlet enthalpies or the exit molar enthalpies? Exit. So what temperature do I need? Yeah. Okay. So you can substitute that into there, and we'll use summations to make it a little bit less nasty to write. FA naught times the summation across all species, the difference between the inlet and exit enthalpies, times theta I, minus, this is all still within the summations, the conversion times the inlet flow rate of A times the delta H of the reaction at that temperature. And again, what temperature?
Exit.
The exit. Yeah, not the inlet.
Would you still have the initial flow rate in that summation? By the initial flow rate?
Oh, you're right. Sorry. This is not inside the summation. Good catch. And you can even see that up here, right? This is all within brackets, and then this is just by itself. So the summation ends after theta I. Yeah.
Question. So if I go to a table to look up the delta H of a reaction,
Yes.
they're not going to have divided the reaction by A, will they? So
No, it's usually going to be as written.
as written, so then you divide it by A to get what we need.
Yeah, you could divide it by A at that point. Yeah. But usually, as written means that one of them is going to be A. Now, if it's the right one, that's where you might have to do some division. And that's usually going to be at like 298. So you'll still have to adjust the temperature, but I think you guys have learned that, how to do that. And we're going to go over it anyways. All right, so if we want to plug all this back into the energy balance, you get that steady state energy balance Q minus the shaft work change in the molar enthalpies times that big theta minus the conversion times FA naught times the delta H of reaction. So notice we haven't, done anything really except some algebra, and we substituted in the equation for the delta H of reaction. Otherwise, we started from first principles just like we would have in MEB, starting with flows in, flows out, and then heat supplied, Q, and then work performed, which is WS. So obviously the thing that we've got to figure out, or remind ourselves, is how to deal with all these molar enthalpies, right? That's what's different here. So the molar enthalpy at some temperature is equal to, what's that?
Standard.
Right. The standard molar enthalpy plus some change in the molar enthalpy. No, I mean, I can't read this. One second. Yeah, QI. No, it can be, but we're not, we're kind of moving past that part. Yeah, it's a little bit simplified. This part, no, I mean, we're still going to have, this is still going to be, that's what you're remembering. Yeah. We just haven't put it on the board yet. Don't scare people with integrals.
What's the TR for?
Reference temperature. Yeah. So usually like 298 is what you'll find in most books is the reference temperature that they'll show you when they're showing you your tables. Yeah.
In our summation on the left board,
Yeah.
just for the fact that at the end we have like less of each component or more of certain components, like the flow change.
Say that again.
Like how do we just for fact like we'll have like less A at the end than we do at the beginning?
That's right here.
Okay, but then will we also have to multiply by the stoichiometric coefficients by that x? We don't have that in the summation.
That's right there. It's all in there. So I mean, you can look at your notes and you can see that all we're doing is algebra. But remember that the first thing that we had when we wrote